Now that we have a better understanding of translational and rotational equilibrium, let's look at all of them together. One of the common misconceptions of students is that students think that they can either exist both together or they both don't exist together. Well, that is not true. In fact, all four situations are possible. And let's look at that. In the first situation where there's rotational and translational equilibrium, one of the situations that we know of is this, right? Where the normal reaction force of the table is equal to the weight, right? Where N equals to W, there will be no translational equilibrium. And since both N and W acts through the center of gravity, there is no rotational moment, right? Hence, there's rotational equilibrium. Let's go down the column. If we have 10 newtons here and 10 newtons here, this would mean that there is translational equilibrium because the upward forces equals to the downward forces. However, there'll be no rotational equilibrium because if we take moments about the CG, we can easily see that this 10 newtons would provide a moment about the CG in a clockwise manner. Let's now look at the column on the right. Are you able to have no translational equilibrium but rotational equilibrium? Answer is yes. Right? If you apply a force of 10 newtons here and apply a force of 10 newtons on the other side, there's no translational equilibrium because there's a net force upwards of 20 newtons. However, if you take moments about the center, about the CG, the moment is actually, net moment is actually 0. Here, there's a special clause, which I put in asterisks over here, is that when an object is not in translational equilibrium, we should consider rotational equilibrium only from the center of gravity. Okay? Lastly, can we have no rotational equilibrium and no translational? Well, that is easy. Just apply a force on one side. This object will both move and rotate at the same time. Okay? With this in place, let's look at some details, some more difficult examples. This was an A-level question that you can actually solve with O-level knowledge. So let's look at this. So a desk lamp is shown in the diagram below, right? And must be constructed such that it does not topple over. Sorry about that. So it does not topple over when it's fully extended. Diagram. Alright, extended in this diagram. The base of the lamp is circular and has a radius of 10 cm as shown here, where my mouse is moving. Other dimensions are also shown on the figure. The total weight of the light bulb is 6 newtons, and the two uniform arms are 2 newtons each, as shown in this diagram. The lamp will rotate about the point if the base is not heavy enough. Mark this point as P. Well, it will start rotating about this point. So this is something that you may not have the sensing, right? But when you tilt something over, it will start to rotate about this point. If you imagine pressing down on this side of the lamp, it will tilt about this point. So that must be the point that you rotate. Next, calculate the moment P, about P, due to the arms and light bulb and shape of it. So taking moments about P, all right, let's find the distance, right? So first, so here is a geometry problem. This is 10 cm. All right, let's zoom in maybe to make our life easier. This 10 cm. The arm is 30 cm. But the CG, the arm, is 15 cm, which means that the CG of the first arm is 5 cm from P. This is another 15. This is another 15. To the next CG. Right? So the first arm is 5 cm away. The second arm is 5 plus 15 plus 15, so that makes 35. P is 35. The last one, the weight of the light bulb, this is how much? It is 30 plus 15 plus 5. That seems to be 0.5 meters away. This is cm. Right, so with this, we actually have a diagram that we can solve more easily. So this is 6 newtons, not 5. This is 2 newtons. Right, so if we look at this diagram now, which is a little bit messy, I agree, we can actually find the moments about P. Right, the first one, the force is 2 newtons. The distance is 5 cm, which is 0.05 meters. The second force of 2 newtons is 35 cm away, so 0.35. The last one is 6 newtons and half a meter away. So the value of the moment is 3.8 Newton meters. Right? So part C, once you have that, you can solve part C. Hence, calculate the weight of the base required to keep it balanced. Well, the weight of the base must provide a moment to keep it in equilibrium. Let's break this down. Hence, tau must be F4 times D, which is the weight of the base. Right? The distance from the base is 10 cm. The rotation moment is 3.8. If you rearrange, the weight of the base must be 38 newtons, which is about 3.8 kg. It's pretty heavy.